Push it to the very edge.
All right, nuclear physics. This is going to be chapter 30. I told you already. So, what were the things that I just mentioned so far?
The number of protons is the atomic number, which is
The representation, right? So, how is the nucleus represented? By using an element is represented by Z, X, A. What is Z called?
Z is
Atomic number, which is the number of protons, and A is called mass number, which is the number of nucleons. Nucleon is a term that is used to say whatever is inside the nucleus. So that is a nucleon. And yeah, so and X stands for the element itself, right? So the X is the nucleus, the name of the nucleus. It can be hydrogen, it can be helium, it can be uranium, it can be whatever. All right. How many neutrons are there? Number of neutrons. There's A minus Z. A minus Z number of neutrons. And the first thing you should understand about this is isotopes. What is an isotope? Something that you must have done earlier. What's an isotope?
The same number of protons, but you have different numbers of neutrons.
Exactly. Nuclei of the same element having different number of neutrons. Okay? So when you say same element, this is the element, and that's the number of protons in the element. These two always go together. Because if this number changes, then that symbol has to change. So these are always together. So that's why it's more important to differentiate it in terms of number of neutrons. So nuclei of the same element but having different number of neutrons, that is called an isotope. And some of the common isotopes of hydrogen are this. These are the isotopes of hydrogen. This is called hydrogen. What's the name of this? What is this called? It's not called hydrogen.
The third is like tritium.
That's tritium or tritium. This is deuterium. Deuterium. This is deuterium. So this is hydrogen. Deuterium and tritium. So these are the three isotopes called differently of hydrogen. The one which is most common is always this. This one is very common, and the other ones are available. There's a lot of deuterium in seawater. So hydrogen, deuterium, and tritium are three isotopes, and they don't always appear in the same ratio of abundance. They come in different proportions. Chlorine, 17Cl35 and 17Cl37 are most common isotopes of chlorine. Uranium, 92 uranium 235, 92 uranium 238 are very common isotopes of uranium.
We're gonna need to know how to find like the molar mass and all that with all these.
We're getting there. You'll have a bunch of calculations required. Right, Jay? What are you doing there? Studying reflection? Okay. Now, if you look into the periodic table and find out what is the mass of chlorine on the periodic table. So, according to this periodic table, the chlorine is 35.4527. The mass of chlorine is 35.4527. Approximately 35.5. and that's what is written as the nuclear mass or atomic mass. So periodic table tells you these numbers. Now this number is using the ratio of abundance they calculated. So it's like chlorine, this one and this one appears in the ratio approximately 3:1. So since it appears approximately in the ratio 3:1, it is 35 times 3 plus 37 times 1, and the whole thing divided by 4 gives you 35.5. That's how they calculate the average atomic mass and nuclear mass. So it all depends on the relative existence of how abundant they are. Now this 3:1 is an approximate ratio, it's not exactly. That's why I said 35.5 is very commonly considered to be a rounded number for this. In reality it is 35.45 something. Okay. Similarly, uranium 235 and 238, they appear in the ratio of 1:140 approximately. Approximate ratio of abundance is 1:140. Which means if you take uranium, most of it is this. Most of it is this. Rarely you find this. But which one is more useful for nuclear fission and all that, which we'll talk about later, is this one. So if you take a kilogram of uranium, the number of atoms that actually can be fissioned out is in the ratio 1:140. So most of the uranium is not useful there. So it's only some of the uranium is useful to produce energy. Okay? So this is a heavy uranium. It kind of absorbs the neutrons. And again, we'll go into details about that later. So the ratio in which they appear is different proportions. And that is what you should understand about isotopes for the time being. So there are different isotopes. There are some isotopes which are artificially created too. Now these are the natural isotopes. There are some isotopes that are artificially created. That means you can actually use nuclear collisions, like take an element, take a nucleus and then bombard it with neutrons or something like that, and then create kind of disturbance, and by which it settles into a new nucleus with a different number of neutrons. So if a neutron is absorbed by a normal nucleus, it will have one extra neutron. So that makes it a different isotope. But those isotopes are not sometimes long-lived. They're short-lived isotopes. Okay? And we'll talk about that also later. All right, is this clear? And these masses are measured by using mass spectrographs. I think you've already seen that aspect, right? Mass spectrometers using magnetic fields. So the mass spectrometers can compare the different isotopes and can measure the mass of the different isotopes accurately. How are masses measured? So what do you mean by atomic mass or nuclear mass? How is it measured? The unit of atomic mass is called an atomic mass unit, or simply 1 unit. 1 unit, or 1 atomic mass unit. So 1 atomic mass unit, that's how they measure the mass of anything. And the definition of 1 atomic mass unit is this. Okay, write down the definition. Definition of 1 atomic mass unit. It's a mass of 1/12 of a carbon-12 atom. It's a mass of 1/12 of a carbon-12 atom. Mass of 1/12 of a carbon-12 atom. That's called one atomic mass unit. Carbon-12. Why carbon-12 is chosen is because carbon-12 is obtained or is available in pure form. That's why carbon-12. Previously, very kind of long time back, they used to use oxygen, 16, so it was based on oxygen. But then they switched it to carbon because it is more available in pure form. So what is this one atomic mass unit? It's a mass of 1/12 of a carbon-12 atom. So what is that representation of 12? 12, we call it mass number. And what is that mass number? It's a mass of one atom, right? But again, how do you, is it one atom? 12 what? Is it 12 kilograms, 12 grams? For that you need to know the connection. What is that 12? 12 represents 12 grams of carbon will be in 1 mole of carbon. 12 grams of carbon. 12 grams of carbon will be the mass of 1 mole of carbon, which is 6.022 times 10 to the power of 23 atoms. So if you take Avogadro number of atoms, it will weigh 12 grams or 0.012 kilogram. So the mass of that many atoms is 0.012 kilograms. So what is the mass of one atom of C12? If that many atoms weighs this much. And this is always true for all elements. Like 92 uranium-238. What does that 238 mean? If you take 1 mole of uranium, it will weigh 238 grams. Right? You understand? If you take 1 mole of uranium, it will weigh 238 grams. So, in 1 kilogram, you will hardly have 4 moles. Right? Little more than 4 moles. That's all you can have for uranium. But for carbon it's different. So mass of one atom is 0.012 divided by 6.022 times 10 power minus 23, or 10 power 23 kilograms. Yeah, I'm not interested because I'm interested in 1/12. So mass of 1/12 of C12 is going to be 1/12 of 0.012 over 6.022 times 10 to the power 23 kilograms, which is equal to 1.66 times 10 to the power of negative 27 kilograms. So that is an important thing to remember. And of course that's provided in the formula sheet, in the data sheet. So one atomic mass unit is 1.66 times 10 to the power of negative 27 kilograms. 1.66 times 10 to the power of negative 27 kilograms. Most of the time you're given the masses in atomic mass units and you have to use it in SI units, so you have to convert it to kilograms before you do anything. Alright, so that number is important. 1.66 10 to the power minus 27 kilograms is the one atomic mass unit. Is that clear? Now, comparison of neutrons and protons and electrons. So, protons, neutrons, and electrons. comparing protons and all that. The first one is mass. Mass, Ethan. Right. Stop. We can stand. That's a pilot's chair. Come on, close your eyes, pilot. Okay, mass. Protons, we say 1 unit. Means atomic mass unit. Neutrons, also we say 1 unit. And electrons is like 1 over 1,822 times a unit. So electrons are pretty light compared to silence. Probably doing a test or something. Okay. So 1,822 units. That's pretty small, light. Now, although we say 1 unit for the mass, it is not exactly 1 unit. I'll tell you the exact numbers. By mass spectrograph, it is 1.007276. 1.007276 units. And neutrons are slightly heavier, 1.008665 units. So neutrons are slightly heavier than protons. Although, on an average, you just say, protons and neutrons are just 1 each. It's not exactly 1, it is this much. So to a high degree of precision, it is this and this. If you take the mass 1.66 10 power minus 27 and divide by 1,822, you should be getting the mass of the electron. Can you check it out? Check that out. Calculate.
Which number? How do I go?
1 atomic mass unit in kilograms divided by 1,822. That will be the mass of electron in kilograms. You get it almost? Should be 9.1 something 10 power.
9.114,
That is exactly what it is. So the electrons are just 1,122 times lighter than an atomic mass unit, which is almost the same as saying this is that many times lighter than a proton or a neutron. So in terms of kilograms, this is 9.11 times 10 power negative 31 kilograms. In terms of kilograms, this is going to be almost 1.66 10 power minus 27, and this also is roughly that, but slight decimal differences. Okay. Charge. Charge of protons, neutrons, and electrons. Proton is positively charged. It's plus 1 e, or 1.6 times 10 power negative 19 coulomb. Neutrons are not charged. Electrons are charged minus 1 e, which is 1.6 with a negative sign, 10 power negative 10 power negative 19 coulombs. That is the charge of protons, neutrons, and electrons in terms of charge. Symbol. Symbolic representation of a proton is 1p1 or 1h1, because once you ionize a hydrogen atom, all you have is just a proton. That's why 1h1 is also simple. But if you know it's a proton, just kind of call it 1p1, that's also good. Now, for anything, what is this bottom number supposed to represent in a symbol? The atomic number, which is number of protons. And the top number? Mass number, which is number of nucleons. That's why it's 1, 1. Also, the bottom number has a different representation. Other than the number of protons, the bottom number stands to indicate the charge of the element. Charge. Like that means 1 here means 1 plus 1. You understand? What is a 92 uranium-230? What does a 92 indicate? That it is a positive charge of plus 92e. You get it? So the bottom number, which is the atomic number, is also telling you the charge of the nucleus. Neutrons are symbolized by the letters 0 and 1. Neutrons take the symbol, yeah.
That's not the charge of the whole atom, though, right?
No, see, there's a confusion always. Try to avoid the. We are talking about the nucleus, so atom will have some more electrons compared to the nucleus, right? I mean, the nucleus is the main mass, but the atoms on it is just pretty light. That's why we don't even bother whether it is there or not. But it does make a difference. So when you are given atomic mass, that includes the number of electrons in it. Nuclear mass excludes that mass of the electrons. So there's a difference between atomic mass and nuclear mass. So this 0 stands for what? Two understandings. There is no proton in there. That's why it is 0. Or charge of that is 0. And this 1 stands for the nuclear number, which is 1 neutron, or the mass. For electron, the symbol is -1 E0. The -1 obviously stands to indicate the charge of -1 E. The charge of -1 E is what is seen over here. And why is 0 mentioned on the top there is because, little mass. It's almost negligible. Compared to this 1, this will be pretty small. What is 1 divided by 1822? 1 over 1822 is 0.0005. Oh, yeah? 0.0005, yeah, which is very light compared to this. That's why it's almost calling it 0. So that's why the symbol for electron takes up this -1 E0. And this is 0 and 1. That's 1 to 1. Okay, got it? So do you have any questions here? Good? So far?
How come the neutron weighs more?
Say it again?
How come the neutron weighs more?
It's because an electron is associated with it. That's why.
Like there's
A proton, you add an electron to it, then the charges cancel off. But the mass of the electron adds up.
but if you add them together it's still not as much as the neutron.
Check it out and see how much it is. It makes a tiny difference.
1.0078 if you add them together.
Yeah, but it's not just the addition, physical addition. It is much more than that. That's what we're going to talk about. Yeah, it is not just the physical addition of masses. It's a lot more to it. Okay? Now, you must be wondering, take the nucleus. What's inside the nucleus? Protons, which are all positively charged, neutrons, which are charged less. So the nucleus, which is such a tiny thing, is bundling up all these protons which are positively charged they should be just exploding because of the electrostatic forces. But why are they stuck together is because of the other kind of force, which is a strong nuclear force. Now, a strong nuclear force which beats the electrostatic force. The electrostatic force is trying to push them away, but the strong nuclear force is pulling them inward. And I think you've done this about forces last year. That electrostatic force, magnetic force, electrostatic, they're all average forces. Nuclear forces are very strong but short range, right? Nuclear forces are strong but short range. They won't act from a distance. They've got to be really close if this is to happen. Even at the same distance, nuclear forces are stronger than electrostatic forces. You can regard nuclear force to be almost like a strong gravitational force. What's the formula for gravitational force? G m1 m2 over the r or d square, right? Now think of how small the d is going to be when you're talking about nuclear distances. They're going to be really small. And so think of dividing something with a really small distance. Even the so-called gravitational force, which is supposed to be a weak force, can be strong enough. So you can regard nuclear forces as a strong gravitational force. You understand? Because it is almost like gravity. Because it doesn't matter what charge it's got. Protons attract protons. Neutrons attract neutrons. Protons attract neutrons. It's all attraction. And as you know, gravitation is all about gravitation, attraction of matter. So, the nuclear forces are binding them together. And that's called binding energy. That's called binding energy. Let's do that in detail. Binding energy. You can write down something about it. It's the energy with which nucleons are bound in the nucleus.
Nuclear what?
It is the energy with which nucleons are bound in the nucleus. It's the energy with which nucleons are bound in the nucleus. Have you done the binding energy thing in chemistry?
No, we didn't do it in that.
Binding energy is the energy with which nucleons are bound in the nucleus. So where is that energy coming from? See? Where is that energy actually coming from? The energy is coming from matter. The energy is actually coming from matter. Last year you've done law of conservation of energy. What is that? Energy cannot be created nor destroyed. They can only be transformed from one to the other. Now you got to define it the right way. The law of conservation of energy and matter. It's a combined thing. So it's not like you can't separate energy and matter. It is a combination of energy and matter. In other words, matter and energy together are conserved. They cannot be created nor destroyed, but they can transform into each other. They can actually change into other forms of energy. So in other words, matter is energy. Matter is energy. Having this wood is energy. Can you get energy out of this? Yeah. You can get energy out of this. So if I take this and burn it, if I take 1 kilogram of wood, and just burn it, okay? If I take 1 kilogram of that one and just burn it, and trap all the atoms that are coming out of it. I don't want anything to be lost. Everything I want to trap. All the atoms, all the small particles, everything I collect and put them together, compact them. After the entire thing is burned, you get ashes, you get everything, right? If you collect everything, you start with 1 kilogram. After you collect everything, how much should it weigh? It will weigh nearly 1 kilogram, like 0.9999 kilograms. What happened to the rest? That rest of the mass is what was changed to energy, the heat energy. So if you're getting heat energy out of something, it is coming by a transformation of mass. Like if you take 1 kilogram of gasoline, okay, petroleum. If you take 1 kilogram of that, you just burn it. Big combustion. And after that, you collect all the burnt gases, the smoke and all that. Collect it somehow and compact it and weigh it. It will be nearly as much as 1 kilogram. Very little difference. And that little difference is the cause for that energy. Make sense? So it's like 1 kilogram is equal to 0.9999 kilograms plus energy. So in matter, energy is conserved. Why I'm saying that is, I told you the mass of the nuclear, the protons and neutrons, right? Mass of protons, mass of neutrons. Those are the mass of protons and neutrons when they are alone, single. When they are single. That's what the energy is. That is not the mass of the protons and neutrons when they are inside the nucleus. So isolated neutrons and protons, if I see a proton here, if I gather it and check the mass, it will be that. But the mass of the protons and neutrons inside the nucleus, they are lower. They are smaller. And that little difference in mass is what is related to energy, according to Einstein's mass-energy relationship, which is E is equal to mc squared. So Einstein gave the energy relationship. The energy here that comes out from 1 kilogram of matter is this. If you can disintegrate that 1 kilogram completely, which is the hardest part. As I said, if you burn this wood, you're literally getting 1 kilogram back. It's a tiny difference. You can't just burn it completely. You can't destroy it completely. In the sense, you cannot just make that thing disappear. Or you can't just make it disintegrate into nucleons. Because that requires a lot of energy. A lot of energy. It's like this. How much energy can come out from 1 kilogram? If you can burn 1 kilogram of wood completely, how much you can get out of it is 1 times 3 10 power 8 squared, which is 9 10 power 16 joules. 9 10 power 16 joules is a tremendous amount of energy. It's not a small amount of energy. 9 10 power 16 joules is probably the energy needed for the entire Louisville electricity needs for 1 week. That's a lot of energy. So we're just having 1 kilogram of wood, and if you can disintegrate it completely, you can supply that much energy. But the problem is, you can't. You can't completely break it down. You still have even the ashes, carbon, they're all there. They're not gone anywhere. It's just that it is just broken down into matter, but a different form of matter, but still is matter again. But only a tiny difference of mass does come into play there, and that's the cause of the energy. It's a tiny difference. So what is the binding energy? It is the energy that is due to the little mass differences. In other words, mass of nucleons is greater than mass of nucleus. Try to understand that term, that statement. Mass of nucleons is greater than the mass of the nucleus itself. You understand that?
You said that was because isolated particles are bigger than.
They have more mass. There are more mass over here than over here, even though they are talking about the same number of nucleons. This has got more mass here, less mass.
So that difference is what you're saying, like the binding energy.
That is the binding energy. That's right. So it's like this. Let's say, AP Physics 2 class wants to create a club. Okay? Now, what is the purpose of the club? The purpose of the club is to make a central point where you all gather together, where you can actually play ping pong, cards, whatever, and, just to get together. Just to get together, it's a club. Let's say there are 40 students who are actually trying to join the club. What's the most important thing that is needed to form a club? Before anything else, first comes what? People, you can,
Moderator.
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 Yeah, I know, moderator.
Yeah, people club.
The most important thing, before you can get, how many people are in this world? Huh?
Money?
Money. Nothing works without. What works in this world without money? First is money.
Kyle.
Yeah, everything is these days, especially these days, everything is materialistic. If somebody is smiling at you, there is some kind of a benefit he's looking for. That's why he's smiling at you. Yeah, there must be a gain coming after that. That's why he's anticipating some gain. That's why there's a smile even. So even a smile is actually costing something.
Wait, why is this one costing something? I missed that.
Because there is always something that's like a give and take sort of thing. They smiled at you, therefore you can expect some favors. So I mean, nobody. I'm just giving an example.
Yeah.
Of course, we do. Of course, so many free services for others. But again, there are reasons why sometimes you end up doing it. As students, you are doing a lot of activities outside. Some of you are doing it sincerely. Some of you are doing it just for the sake of getting those hours. Yes? Yeah, you just want to get the hours, and that's why you go to the soup kitchen, you go here, you go there, and try to get those hours. And once the hours are done, you say, I'm done. Or to get into GSP. You want to make sure that your application looks good. So you want to create those big list of service hours. Even if you do X number of hours, you make it twice of that on paper. But, I know that. So all this is basically, that's why you do it. But hats off to the one who actually does it without any returns. Absolutely. No returns expected. That, of course, is different. Okay, so, yeah, in this world, so many things happen. So, to form the club, what do you need? Money. Because you need money to actually, rent a place. You want money to buy a ping pong table or a flight simulator, or you want money to pay for electricity and all those things, right? So you need money for that one. So therefore, the moderator of this club, let's say Jay takes over the moderator position, and he says, all right, we're going to form this club of 40 AP2 students, and so everyone bring $200 tomorrow, because the club needs to be formed.
It's a little stupid.
Well, you need to form a club. So everyone comes with $200 to form the club. What's this? They all come with $200 in their pocket. And then they get together to him. And then they say, all right, here's my 200. So they surrender their $200. And then they become part of it. He writes the name. Okay, done. So now you become part of the club. Right? Remember, you were heavier before you were part of the club by $200. You're richer by $200 when you're outside. But when you join the club, you're $200 poorer. Make sense? You had more energy before, you had more mass before, but when you join the club, your mass dropped a tiny bit. And that tiny bit is used for the bonding purpose. You get it? So the club is formed. What's the total binding energy for this club? 200 from each 40 students. How much? $8,000? Yeah. So he will invest in the right place. He won't waste it. He will invest in the right places and then get the profits from everywhere. And because of the profits, you keep paying your rents and stuff like that. And then club runs fine.
What club is this?
AP Physics 2 club. You got it?
It's a study club.
Now, look at this. People who are inside the club, they have less matter with them. Outside, they had more. Now, this is my example purely. It's not in a book or something. So, I had to come up with these examples starting with my first year of teaching. Because I said, like, okay, if I'm saying something about nucleus and all that, I always want to like really understand those things unless I look for some examples. So I found this to be a good example where I can actually talk about that example and something that you will never forget for life. Because I've had students turn to me after 20 years and said, the example you said about this, it's still in my head. It should be. That's how these examples are supposed to help you with the subject because it makes it easier to understand. Examples are always useful. All right.
Coleslaw.
So, huh?
Coleslaw.
Yeah, I know. Listen up. So you were $200 richer outside. That means the protons and neutrons outside were heavier, but when they joined together to form the nucleus, they surrender part of their mass, and that mass is what is used to the binding energy part of it. Okay? Now let's say, as you are functioning nicely as a club and everything is going well, I step in and say, all right, the club's name is AP Physics 2, right? That's mine. Okay. I want to break this club up. I don't want this club in existence. So I want to break that club up. What will you say?
Paid mine.
Huh?
Want my money back.
Give my money back. Exactly. Because the money is what is holding you inside. The binding energy for everyone is that money that you contributed. You can't just run away. That means like you lost. So when he asked me, give my money back, I'm coming now with $8,000 because my goal is to break you up. So I'm saying, all right, here's $8,000, 200. Take it out. Can you go now? Yeah, I'm going. Don says, I'm happy. I got the money back. You understand what I'm saying? So if a nucleus is bound because of a binding energy, you need to provide that binding energy in order to split them up. If a nucleus is bound with a certain amount of binding energy, you need to provide the same amount of energy to split a nucleus up into nucleons. That's a lot of energy for each nucleus. Think of that. It's per nucleus. How many nuclei are there in a certain mass of a sample? That's a lot. So therefore, the amount of energy involvement is a lot. So to get it split into nucleons completely is not a joke. It's a lot of energy. That is why I said the mass outside and the mass inside are different. You understand that part? The mass outside and the mass inside are different. So how do you actually find out the binding energy? The binding energy is actually found like this. Mass of nucleons. So if you have an element ZXA, how many protons are there? Z number of protons of each of mass MP. Plus, how many neutrons are there? A minus Z number of neutrons times Mn. This is the mass of the nucleons. And that minus the mass of the nucleus. That's the mass of the nucleus. Will give you an amount of mass difference. And that is called the mass defect. Finish the test. That's called mass defect. And that mass defect times c squared is the binding energy. So if you take the mass of the nucleons minus mass of the nucleus, you get what is known as a mass defect. And that mass defect times c squared will be the binding energy. Alright, now we are doing an example for binding energy of helium. So let's find the binding energy of helium. Binding energy of helium nucleus. I'll give you the stuff. You already know the mass of? You already know the mass of? Mass of neutrons and protons you already know. And the mass of X, mass of the helium itself, is 4.001505. Now go ahead and find out.
Do you want us to use one ANU for protons and neutrons?
No, you have to use the actual ones.
The actual ones.
Yeah. So the number of protons here is 2. 2 times MP plus 2 times Mn. This is the mass of the nucleons minus mass of helium is equal to delta M. So get the delta M first. You already have the mass of proton 1.007276 and mass of neutron is 1.008665. Surely you'll get a mass defect. And then get the energy. How much is this?
Oh, delta M.
Oh, so no. I mean, I don't want delta. Tell me the Tell me the binding energy.
2.7 times 10 to the
2.7.
7.
Did you change mass to kilograms?
No.
Do that. Because you're taking the speed of light as 3 × 10⁸ meters per second. So you have to take the mass, which is in atomic mass units, times it by 1.66 10⁻27, and then do your c square.
You should.
How much?
4.5 and then negative 12.
4.5. Anything more?
10 to the negative 12.
0?
Oh, 4.54.
10 power negative 12.
Yeah, I'm confused. Mr. Sam, what do we do to the delta M after we get it?
You multiply by 1.66. So how much is delta M? I'll do it here. How much is
It
delta?
was 0.03037.
Multiply that with 1.6610. This is units. Multiplied by that much, and that will give you in kilograms. And then use that in this equation B is equal to delta MC squared. And that will be this energy. Now, when energies are so small, you don't normally express in joules. What's the other unit used for measuring small amounts of energy? Electron volts. So convert this to electron volts. Go ahead. Convert it to electron volts now. How much?
2.8 times to the
2.8?
7 times 10 to the 7.
2.85?
2.84.
Is it 2.84 or 2.85?
Good 2.84.
Also? Positive 7, right?
Yes.
Now, when you express it in electron volts, this looks like a big amount of energy. So then again, we use prefixes. And now, million electron volts, mega electron volts. How much is it? 28.4 million electron volts. That's how we normally express binding energy. All the binding energies for all the nuclei, we normally express it that way, in million electron volts.
Okay, so you got
1 MeV. One MeV is like 1.6 10 to minus 13 joules. That's the relationship. So we get 28.4 MeVs, which is the binding energy of the nucleus of helium. Now, what do you think is the binding energy of uranium? Oh, definitely high, because you're talking about so many nucleons, right? The binding energy of uranium, because there are 238 nucleons, is supposed to be pretty high. If this is if this is 228.4, the other one's going to be in thousands. It's going to be in thousands. So uranium is like a club. Uranium is like a club, and that club is called not AB Physics 2. It's the Trinity Club. So imagine someone decides to form a club which is called the Trinity Club.
It's a bigger deposit.
So someone is starting to collect money, and how much he's collecting from 2,000 students is like $10. Yeah. He's only collecting $10. What's the example? He's collecting $10 from each member, and there are 2,000 students, let's say. How much is total binding energy? 20,000. So the whole school's binding energy is 20,000, whereas your class club is 8,000. So which binding energy is bigger? Which binding energy is bigger? Obviously the whole school's, yeah? But where are you going to be more stable? Where are you going to be stable? Where are you going to be felt important? Here. Here you're going to be felt more important. Say one day, Ethan is not there. Immediately, what happened? He's missing. Call him. Let's find out what happened. Everyone's concerned about your absence. You understand what I'm saying? Nobody, everyone is kind of looking at who is missing and immediately finds out who is missing. Yeah. So it's easy to find out who is missing, and because the club is bonded in a different way, it's not because binding energy is only 8,000, but the binding energy per member is bigger. You get it? The binding energy per member is bigger. So what causes the stability of a nucleus is the binding energy per member. It's not the total binding energy. It's not the total. Like the Trinity Club, who cares if you're absent for 2 months? Nobody will understand. Nobody will know who you are. And so even if you're absent for 2 months, nobody's going to feel that you're missed. You understand what I'm saying? So that's what happens if it's a larger club, and if your contribution is like small, then you're not really, you don't care. You don't really care. It's less important sort of. So uranium, although it has a lot of binding energy, the binding energy per member is smaller. And that's where we define what is known as binding energy per nucleon. This is called binding energy per nucleon. Binding energy per nucleon means what? You divide it by the total number of members. So in your class there are 8,000, so 8,000 divided by 40. That's $200, right? 200. What about the Trinity? 20,000 divided by 2,000, which is $10. So you're worth only $10 when you're actually in the school part. So the binding energy per nucleon is more important. So how much is the binding energy per nucleon for helium? 28.4 divided by 4, because there are 4 nucleons in the nucleus. So 7.1 MeV. And if you work the same way for uranium, it will be lower than 7.1. You understand? So helium is pretty stable. Uranium is not really that stable, because the stability is decided by this factor, which is the number of binding energy per nucleon. That's one factor. Stability is not based on only one factor. There are multiple factors also. I'll explain to you that. So binding energy per nucleon is one factor which decides the stability. The other factor that decides stability of a nucleus is neutron-proton ratio. Neutron-proton ratio. That's also an important factor. The neutron-proton ratio is another important factor. Those which contain the same number of neutrons and protons are very stable. Like helium, 2He4, very stable. So the binding energy per nucleon is 7.1. That's pretty stable.
It's He.
Yeah. 2He4 is very stable. 6C12, very stable. 8O16, very stable. Anything that has equal number of protons or neutrons, they're pretty stable. So on a graph of neutron-proton ratio, the graph is initially a straight line with a 45-degree angle. So this is the ideal line. You can see that initially all of them nearly have equal numbers of protons and neutrons, but as they get heavier and heavier, they deviate. So the deviation takes place like that, and then goes like this. What are all those dots?
The actual values for each different atoms.
Different atoms. But if we count this, it's going to be far beyond the number of elements.
The number of isotopes.
Isotopes. So these are all the isotopes. These are all the different isotopes. And you can see some of these isotopes are on this side of the line, and some isotopes are on this side of the line. The general rule is this. Think of this. Husband and wife. Imagine there's an apartment where you have one husband, one wife, another husband, another wife. They just share that apartment. Pretty stable, right? Imagine there are 3 couples. Pretty stable. When is the stability disturbed? Is when, imagine there are 2 couples and then one extra lady in the house. That will cause all the mess. That one extra lady's presence will cause total instability, right? The whole thing is going to be unstable. Instability is caused mainly from that one extra neutron. That is why neutron-proton ratio, as long as they are equal, they are okay. As the number of neutrons go higher and higher, stability becomes bad. So I just always give the example of protons being us, and neutrons are the extra ones that are coming in. They are the ones who cause all the uncertainty. They are the ones who cause it. So now, to make something unstable, you can also do it artificially. You can also cause stability problems. So what is going to happen when a nucleus is unstable? When a nucleus is unstable, which means what? It is angry. What will a nucleus do? If I'm angry, what I'll do is I'll take this whole book and throw it at you, right? That's one thing I can do. Or then I'll see markers, I'll throw the markers. That's the next thing I can do. If nothing is available, I'll just say, right? 3 things. The first is called the alpha particle. The second one is called the beta. And the third one, just a puff of energy, is called a gamma photon. You get it now? So when a nucleus is unstable, it emits 3 radiations, 3 kinds of radiations. Normally, it collects 2 protons and 2 neutrons together from the nucleus and throws it away. That is called the alpha particle or alpha radiation. Beta radiation is when it throws an electron. I'm going to talk about that in the next class. The electron from the nucleus. Come on. How many electrons are inside the nucleus?
0.
That's what I'm going to talk about in the next class, okay? There are 0 electrons in the nucleus, but still the nucleus takes an electron from inside and flings it out. That's the beta radiation. And the third one is the gamma radiation, which is basically something that makes you absolutely cool. Like imagine this, if you're unstable, you're angry, try this at home. Don't try throwing things around. Instead, take a deep breath and puff out that energy, and you'll feel. What's that? 2 protons and 2 neutrons. It's a helium nucleus. Yeah.